Hello and welcome back to Engineering 211 Statics, and I wanted to go back and pick up a section that we had purposely skipped over, that is distributed loads or distributed loading, and that you'll find it at the end of Chapter 4. I'm not going to be any more descriptive than that because it depends on which edition of the textbook that you have, but go to the end of Chapter 4 and you'll probably find that. You may want to look and see what your author has to say about that. But to some extent, maybe we haven't been completely realistic or honest in our models. Let's say that we had a wheel and we placed a load on it like this, a concentrated load. If we were to try and improve that model, what that model looks like, maybe it looks like, we should make it look like this, where it's got a load that might be distributed over this. Certainly if we have a radial tire, this is going to be a much better model. If we have a bias pie that's all pumped up, or certainly a steel tire or something like that, then maybe that's an okay model. Even recently with our structural work, we took a two-force member and said that maybe we had some compressive force in it, acting like this, and eventually, this is not bad for depending on what we want to do with it, but eventually we're probably going to think about this as some load distributed over the surface of the hole, the bearing of the hole there, and then some load distributed like that. So we'll talk about this a lot in strengths of material, third term. But for a lot of our structural analysis, I mean, this one works just fine. Where we really need to think about a distributed load is when we get into things like dead loads or snow loads, maybe in a building. Let's say that we have a building, and I'll keep it really simple here. We've got a nice flat roof, or virtually flat, and if we look at snow on this, it's snowed, and we have snow out here. We would want to model that certainly with a distributed load. Another place that we'll get into distributed loads is if you look at a dam, and maybe we build a earthen dam or something like that, and we have water there. We'll have a distributed load that looks something like that. You recognize that as you go down in water, the pressure increases. And to some extent, the civils will get into something that looks a lot like this when they build soil retaining structures. Let's say that you have a hillside that looks like this, and you want to take better advantage of it, so you come in here and you put a retaining wall in here. That's going to look something like this. And then you can take and maybe I'll change pens here a little bit so we see this. So you're going to change the soil profile so it looks like this, and then it looks like that. Maybe you're doing some sort of terracing or something like that. And when you do that, you're going to have a pressure profile on this that's going to look like that. So all of these cases deal with distributed loads. So we want to be able to talk about that. So let's see if we can. And again, you'll find this at the end of Chapter 4 in your reading. We're going to develop this with a simply supported beam. You could do this with a cantilevered beam if you wanted to, but I'm going to do a simply supported beam. And we'll say the beam is like that. We'll say it's got a pin connection here and a roller over here. I'm going to say in this direction we have our load W, and maybe it has something like this. So we've got this distributed load. Maybe it's a triangular shape, constant shape, trapezoidal shape. I'm not sure what shape that's taken on, but we're going to say that W is equal to W of X, where this is the x direction. Okay, so it's some function of x. And I'm going to cut out a little piece here, and I'm going to say that this is dx, and I'm going to say that this distance here is x. And of course, maybe we'll take the whole thing as some length L. So if I talked about the force on this, if I wanted to talk about the force on this element here, I could say that that was dF, which is going to be equal to W of x times dx, right? Essentially, that's the area above this thing, right there, which would really be equal to, as I said, the area. Let me call that dA. So I could say that F, the total force here, is really just the area, the integral over the area, or I'll say the integral of dA, the area integral. If I wanted to say that a little differently, I could talk about the resultant force, the total force, the sum of all of these individual forces, as the sum of F, which would be the integral from 0 to L across this whole thing of W of x dx, which is, again, really just the area, the integral over the area. Okay, and in plain English, this is the area under the curve. Okay, and while I've got some odd curve here, a lot of times the curves are fairly simple and it's fairly easy to find the area. We may not even have to do calculus to do that. Well, depending on where this is, I mean, you could imagine if this was a shape that looked something like this, that force, this equivalent force, is probably not going to be acting at the middle. It's probably going to be heavier down there. So we want to try and figure out where that is. And we're going to assign this dimension. We're going to say that this is x bar, where that equivalent force is located. Okay, so if I go through that, let me go back to this example a little bit and think about the moments here produced by this. And if I have then, I think about the shape here, I'm going to have some resultant force, F sub r, and I'm going to say that's going to be located at some x bar. And I'm going to reference everything to here. This will be my reference. Okay, and I can say if I want to sum the moment about the reference, that has to be equal to 0. So I have to say that x bar times f sub r would be equal to the integral over the area of x dA. If I were to take each one of these little differential elements here, that's dA, and multiply it by its x, and sum that up, that should be the same. So I can say then, solving for x bar, that x bar is equal to the integral over the area of x dA divided by f sub r. And what's f sub r? That's the integral of dA. So we have the integral over the area of x dA divided by the integral over the area dA. Okay, so we'll remember that. Maybe I should say that's x bar. That's worth keeping track of. So let's take that and try it on a fairly simple problem, one that we probably know the answer to, and see if this works. So I'm going to say, look at this example here. Again, this should work on cantilever beams, but I'll start out with simply supported beam and say that I have this distributed load. Like this. And I'm going to say that W of x is equal to 100 pounds per foot. So each foot of that, we have 100 pounds on. It'd be like if you had a box that was 12 inches in dimension, a foot in dimension, and it weighed 100 pounds, and you started setting those boxes on here. That's what you got going on, 100 pounds per foot. And sometimes we'll talk about, and I learned it as this way. I learned that as Q of x. Okay, so sometimes we use W of x. Your author will be using W of x. for the distributed load, but sometimes people use Q of X, and sometimes I may slip back into that because that's actually the way that I learned it. And let's say that this is 10 feet long. Okay, so I guess we could look at the answer of this thing. We know that the area is going to be equal to 10 feet times 100 pounds per foot, which gives me 1,000 pounds. So we'll expect to come up with an answer that F sub r is equal to 1,000 pounds. And where is that going to be acting? Well, it actually acts at the centroid of that thing. So this will be at the centroid. And where's the centroid of that rectangle? Should be at the center, so that should be at the centroid, which is equal to 5 feet from either end. Okay, and we haven't necessarily talked about centroids yet. We will be getting into that later in the term, but most people recognize the centroid for a rectangular region is going to be at the center line there. So we'd have the centroid located there. If we look at a triangular region, where's the centroid for a triangle? You've probably done this in math. It's going to be 1/3 from the large end and 2/3 from the small end. So we'll use those to our advantage today. Well, anyway, if I were to go through the strict math and look at the equation here, I can say that the integral over the area of dA is really just equal to what? The integral from 0 to 10 of 100 pounds per foot, then dx, which gives me what? 1,000 pounds. Okay, so that seems to hold true. And then if I look at x bar, that's going to be equal to the integral of x dA divided by essentially this thing, the integral of a dA. So I could say that integral from 0 to 10 of x times 100 dx divided by, we don't need to do this again, we'll just say that this is equal to 1,000. So this turns out to be equal to what? X squared over 2 evaluated at 0 and 10, and then I'm going to have what? 100 divided by 1,000. That 100 would come out as a constant. So I have 10 squared 100 over 2, which is 50. Nothing on the lower limit. So I have 50 times 100 divided by 1,000, which gives me what? Should be a tenth. A tenth of 50 is 5 feet. So we see that also. So you're probably on a simple problem like this not going to go through the calculus of this. But I think it's always good to take a problem that we know the answer to up here and try our calculus on it, because sometimes if we get into a problem that is a shape we don't recognize, this calculus can be useful. I mean, where do we get into that? Certainly a lot of times with snow load, we'll try and use some simplifications. Like we started out our discussion with, if we just have a flat roof, we're probably going to just take a constant load like this, so we're not going to be doing a lot of calculus with that. Maybe if you get something like this where you have a building and you have a awning out here, you can get some drift here like this, so maybe you'll get a distributed load that would be a triangle. If you have material, so you get some sort of a chute and material is coming here and landing, maybe you'll have some sort of a pile like this. You'll get a exponential or sinusoidal shape like that. Although a lot of times we might just approximate that as a constant load that looks like that. Depends on how good of an answer we want. Okay, if we're talking about just the floor in a barn or something, we might just reinforce it and take a maximum value and be done with it. If we're talking about something we want to have a lot more sophisticated design, something where weight and cost, weight is a big issue and cost maybe isn't a big issue, maybe we'll go through the calculus on something like that. So all kinds of places where we see these. Well, let's try another one. And this one's going to be a trapezoidal load. So and I'm going to say that it goes like this. It goes from 50 pounds per foot back up to 100 pounds per foot. Like that. This is 9 feet across there. So we'd like to come up with the equivalent force and where that equivalent force is located. So we find F sub r and x bar. That's what we're trying to find on this thing. Well, I probably need to find the equation for this if I'm going to use calculus. And we'll do this a variety of different ways. We may not necessarily need calculus, you'll see when we get done. But if I want to come up with this w of x, what's that going to look like? I could say that that's equal to, does this have a slope? Yeah, minus, 50, because it drops 50. I have a drop of 50, so minus 50 over a run of 9 times x. So if I put, if I take x equals 0 here, I get, I better add 100 to this, right? So now, if you take x is equal to 0, you're going to have 100. If you take x is equal to 9, you're going to have 50. So that would be our equation, 50 over 9x plus 100. And a lot of times I'll do that. I'll just take the shape of this and then play with it until I get the b term. Y is, of course, y is equal to mx plus b, or the y-intercept. If you wanted to, I mean, you could use the point method. You have a point here at x equals 0 and 100, and then you have x is equal to 9. This is x is equal to 9 and 50. You got 2 points. You could come up with the equation. So however you want to do that. Well, let me take that equation then, and I can use it to find the area under there. I could say that f sub r is going to be the integral from 0 to 9 of 100 minus 50 over 9x dx, which gives me what? 100x minus 25 over 9x squared, evaluated at 0 and 9. Is that right? Yeah. So I have 100 times 9 minus 25 over 9 times 81. My lower values are 0, plus 0 if you want. So this turns out to be 675 pounds. And let me double check that. I'm pretty sure that's right. Yeah, 675 pounds. Okay. So that would be f sub r. And we want to find out where that's acting at. I mean, there's f sub r there. And we want to find out where that is acting at this x bar. Okay. So I can get x bar. I could say that x bar is equal to, what am I going to have here? The integral from 0 to 9 of 100x minus 50 over 9 x squared. I've multiplied this, I've essentially taken this and multiplied it by x. I have then dx there. And then I have to divide this by what? This thing, which is 675. So when I go through this, I'm going to come up with what? 1 over 675 times 50 x squared minus 50 over what is that, cubed 27. All right, yeah. X cubed, is that right? So 3 times, yep. And this will then be evaluated at 0 and 9. So I have what, 50 times 81 minus 50 over 27 times 9 cubed. Then you have to divide the whole thing by 675. So what's that turn out to be equal to? Four, yeah. 4 feet. So that's X bar. Does that seem reasonable? I mean, the center point would be 4.5. It's heavy on this end, so we'd expect it to be smaller than 4.5. So I think that that makes sense. And again, our calculus method proves accurate. Now, a lot of times you start doing consulting and stuff. You don't want to go through calculus every time. So we could actually break this up a little bit differently. I'm going to try this a couple different ways and see how this works. So I'm going to do this as a constant load. So that's just a rectangle. And then I'm going to put a triangle on top of it. Okay. So I know that the area of this thing, this is going to be 50 pounds per foot. And then I have 50 here, and I have another 50, which gives me then a total at that point of 100, right? Pounds per foot, pounds per foot. Okay, so I could say that the area under there was equal to, this is being, again, 9 feet, same problem, is 50 times 9 plus, that's the rectangle, another 50, that's that side there, 50 times 9 divided by 2. Got to divide it by 2 because it's a triangle, right? So what's that turn out to be? $675. So that was a little faster than the calculus. Now, where is that acting? Well, what we're going to have to do is we're going to look at this. And I essentially have this rectangle that's acting here. Okay, and then I have this triangle, and it's acting over here. Okay, we said the rectangle would be acting at the center of the rectangle, and the triangle is at the 1/3 point. Okay, so I could say that I have 675 times x bar would be equal to the area of the rectangle, which is 50 times 9, that's 450, right? 450, and what distance is that acting through? That's acting at halfway. This halfway point is 4.5 plus, what's this, 225? Okay, that's the area of the triangle, and that's acting at 1/3. That's 1/3 of the distance, 1/3 of 9. So 9 over 3. So I could solve x bar with that. I take this and divide by 675, and what do I come up with? 4. Okay. So that's when you're out in practice, that's what you're probably going to do if you've got some standard shapes. Now, having said that, a lot of times civil engineers, they like to think of things as triangles. So let me try it again. So I'm going to think of this thing a little bit odd. I'm going to think of it as a triangle here where this side is 50. And I'm going to think of it a triangle that looks like that where this side is 100. Okay. And again, I could say that the area is going to be 100 times 9 divided by 2 plus 50 times 9 divided by 2, which gives me what? I mean, again, this is what, 450, and this is 225. So 675. That works. And then, where are these forces acting? Well, I've got this one here. This is going to be that 450, and that's going to be at a third from this distance, so you've got 3 feet there. And then I have this, which is that 225, which is at a third of this distance, 3 feet. Of course, that 3 feet comes from 9 divided by 3. 9 over 3. That's where that 3 comes from. So I could say then that 675 times x bar is equal to 450 times 3 plus 225 times, and I have to be careful of this, I've got this 3 distance from there. This total distance is 9, so I need to say 9 minus 3, right? Because I'm finding it about this point. This is my reference point at the left-hand side. So with that, x bar turns out to be equal to, when we solve that, take this right-hand side, divide it by 675. So when you see someone dividing it up like that, that's what's going on. So these are probably the ways that you're going to do it. You're not necessarily going to go back to the calculus unless you get something that is a sinusoidal or exponential or something like that. Okay. Well, let's move on. Let me try one last problem. And this is going to be a dam problem. So let's say that we have a dam here. And we have water up there. We'll say that it's fresh water. And I'm going to take that this is 32 feet. Okay. The reason I take that for 32 feet, if you have any scuba divers and whatnot, they'll probably recognize that's about 1 atmosphere with fresh water. Okay. So if I look at the pressure distribution here, if I look at a gauge pressure, I have 0 psi at the surface, and down here I have about an atmosphere, 14.7, or why don't I just call it 15 psi there. Anyone that's maybe gone down and stood on their head at the bottom of the public pool or something recognizes there's more pressure at the bottom. Your ears hurt more there than at the top. So let me take this pressure distribution, and incidentally, the civil engineers that go on to do earthwork and whatnot, when you look at that retaining wall that we saw at the beginning of lecture there, and you looked at the this is the heel and the toe. Usually the heel's a little bit longer, like that, if you have the space. So you put, because you got the weight of the soil acting down there, holding that and resisting this pressure distribution here. That's probably going to look something like that, right? And a lot of times this is some fraction of water. You put some drain in here, you put a pipe in there to try and keep this drained out so it's dry, and then you'll have some fraction of water. You don't want this to liquefy in there. And there's lots of things that when you go to soils, you're going to talk about active pressure or passive pressure, whether you're allowing this to rotate slightly and whatnot. So a lot of good stuff there. So even if you don't get into the business of building dams, you use these concepts a lot when you deal with soil pressure. So let's continue on with our work here. And I'm going to take a dam that's 1 foot into the page. Okay, 1 foot into the page. So if I have 0 psi times 12 inches gives me 0 pounds per inch. Because 1 foot, that is 12 inches. Okay. And here, if I take 15 pounds per inch squared and I multiply by 12 inches, because I'm doing 1 foot into the page, and you might say, well, no one builds a dam that's only a foot wide. Well, that's true, but we can take our conclusions here and then multiply by how long or wide the dam is. So with 12 inches, I come up with what, 180? I believe. Yeah, 180 pounds per inch. Now I have to be careful, I'm in pounds per inch, not pounds per foot. So what's this going to look like? I want to turn this in to something that looks like this. I want to come up with an equivalent force, and I want to figure out how high that force is acting. X bar. Okay, because this equivalent force is important. If I don't want this dam, you don't want the dam to slide down the valley. That's a big a problem. And this x distance, this is important if we start talking about the moment and talking about the dam turning over. You don't want the dam to turn over, to tumble. That's a bad day, and you also don't want the dam to slide down the valley. So both of those numbers are important. Well, we can really just get the area there. I can say that this is 180 pounds per inch times 32, because 180 is this side, 32 feet is this side. I have to multiply this by what? 12 inches in a foot. Got to be real careful with our units, because if we weren't, we'd be off by a factor of 12. And I'm going to get to cancel that with that. And of course it's a triangle, so I'm dividing by 2, right? So as we go through that, that turns out to be what? $34,560 pounds. I've got too many significant figures there, but I'll leave them so you know where that number came from. You can check it out. So 34,560 pounds. And what's x bar? Well, x bar is just going to be equal to 32 feet divided by, it's going to be acting at the centroid. We know the centroid for a triangle is 1/3 from the large end and 2/3 from the small end. So I'm just going to take this and divide by 3 or multiply by 1/3. 32 feet times 1/3 gives me what? 10.67. Let's say 10.7 feet. So with those two numbers, I could start to design this thing. Now, some of you might be saying, this is a fairly large number. Yeah, it is. The force that dam has to resist is incredible. Remember, we're only taking a dam that's a foot into the page. Okay, you start looking at something like Detroit Dam or the dams that we have around here. These numbers are going to go up incredibly. So, yeah, good exercise. Speaking of the Detroit Dam, I think we sometimes take that for granted. Let's look at Detroit. So the Detroit Dam is the length is 1,523.5 feet. We'll just call it 1,523 feet. So now multiply these numbers with 1,523, and then the height is not 32, but rather 463 feet. Okay, so I think it's about the 14th tallest in the United States. It's a pretty good dam. Fortunately, it seems like always just busy passing traffic as we go past it, but it's probably worth taking a look at sometime. Big Cliff, if you want to talk about Big Cliff, that's the dam below it. Now, a lot of times they'll put dams in pairs to help with flood control like that. So there is Big Cliff. And it's not shabby. It's 280 feet long. It's in a much tighter canyon if you've noticed it, and the height, this being the height here, the height is equal to 191 feet. And they make some electricity there. I think I went to the Corps of Engineers page, and I think the Detroit Dam is about 100,000 kilowatts. So let's see, 1,000 kilowatts would be a megawatt, so it's 100 megawatts. Okay, and Big Cliff is about 18,000 kilowatts. And those numbers probably don't mean much, but if you think about the trash burner, right there in Brooks, the trash burner is about 13 megawatts. Which is going to be 13,000 watts. So it's on par with the Big Cliff Dam, still much smaller than the Detroit Dam. And this is about the consumption of a town like maybe Woodburn. Okay, something like that to give you some idea. So we get quite a bit of electricity from that, but the dams were certainly built for flood control. We had terrible flooding before we had dams on some of the tributaries like that. Well, the problem that you oftentimes get into when you consider these tremendous loads is they always have a problem where a car goes off the road and is in so much water, and they give you the size of the car door and how deep it is, and you have to figure out what force it would take to open that door. And you could imagine it would be incredible. So that always comes up to the trick. Then how do you get out of the car? The MacGyver types in here realize that you have to somehow open a window or break a window, get it broke out, and get the car full of water so that you equalize the pressure. Because if you look at, we've got enough spot here. Let's say you look at the car door here, and we'll say this is your car door. I'm not sure which is up anymore because it's fallen in, but there's the hinge, and you have a pressure distribution, which maybe looks like this, depending on how it's oriented in the water. You have thousands of pounds on it. Your only hope is to get an equal pressure distribution over there by letting the vehicle fill up. So you let it fill up with water, which is probably not good for your habitation of that anymore, but hopefully then you can get the door open quickly and get out. I always make the joke that you just crack the window and relax and let it fill up with water while you're smoking a cigarette. When the cigarette goes out, it's time to get out of the car. Hopefully the pressures have equalized by then. So he'll tackle both the mechanicals and the civils. We'll tackle more problems like this, and it's all about distributed loading. So that gets us to a good starting point. We've gone back, we've finished up that material on distributed loads, and we're set then to move forward and look at internal forces. When we start talking about spring term, what's an internal stress and strain and things like that, we're going to need to know those things. So that'll be an interesting section as we go forward and start looking at internal forces. So thank you for watching, and take care till then.